All right, Chem Squad, here's a little bit of help for your calcium learning over colligative properties and parts per million. A couple key things to remember when we're talking about colligative properties. It's all based around changing the properties of your solvent when you dissolve or create a solution with it. And primarily you're going to see it based around aqueous solutions of water, and boiling points will always go up when more things are dissolved into water, and the freezing points will always go down when more things are dissolved in water. All right, so let's take a look at a few of these questions, see if we can help you out. All right, so the first one comes up. Compared to the freezing point and boiling point of water at 1 atmosphere, a solution of salt and water at 1 atmosphere has. So there's our key thing, is that we are comparing water, plain water, so that would be H2O as a liquid notation, to salt water, which if that we were to write that as a formula would be NaCl, and then it would have the AQ for being aqueous. So we're comparing those two things, which means we have pure water with nothing dissolved in it and water with salt dissolved in it. And based on what we talked about with colligative properties, we know that as soon as we dissolve anything into water, the boiling point is going to increase and the freezing point will have a depression or decrease. So it'll freeze at a lower temperature, boil at a higher temperature. So the best answer we're going to look at here shows that we have a lower freezing point, higher boiling point. Answer choice 2. And again, most of the ones we're going to deal with here in our first chemistry class is going to be focused around examples with water. All right, next, which concentration of a solution of CH3OH in water has the lowest freezing point? So again, we're looking at a solution in water, and we know that if we add something to water, the freezing point goes down. Now they're asking about changing the concentration. And we talked about in class, if you increase the concentration, you're going to have a greater effect on the change in properties. So in this case, if we're talking about the freezing point, that means if we increase concentration, the freezing point is going to decrease more. So we're going to look for, in this case, which solution or which concentration value that we're given over here is the largest. And these questions can trick students because they're giving you all concentrations, molarities, that are lower than 1. So a lot of times what happens is students will read this too quickly and they'll instantly circle number 4 thinking that's the largest concentration or the highest concentration, when actually that's the lowest concentration. So our best answer in this case was the one with the highest concentration, which would be choice 1, because that's at 0.1 molar. All right, next one in line here. Compare the freezing point of 1 molar KCl solution. We know it's solution because it's got the AQ at standard pressure to the freezing point of 1 molar CaCl2 solution at standard pressure is. So we're comparing two different types of solutions, but they have the same concentration. So now it matters as to what exactly we are dissolving. So we have KCl and CaCl2, so potassium chloride and calcium chloride. Now both of these, if we look at them, have a metal in front and then the non-metal chlorine. So a metal and a non-metal, we know that that means they are ionic compounds. And if we take these and dissolve them into water, we know that they are going to dissociate. So now the key is which one of these dissociates into more ions or splits apart into more ions when they dissolve. So think back to the simulation we looked at in class. When we put these ionic compounds or salts into water, they split apart into ions and actually make more particles. So potassium chloride, when it dissociates, will give you a K plus ion and 1 Cl minus ion, and both of these would then be aqueous. So there's its dissociation equation for potassium chloride. So when that splits, we get 2 moles of ions. Calcium chloride, on the other hand, when that dissociates, that's going to create 1 mole of a calcium positive 2 ion. And since we have that subscript 2 there, that's going to give us 2 moles of chlorine ions, or chloride ions. So because of that, calcium chloride actually produces 3 moles of ions, 1 calcium and 2 chlorines. So because calcium chloride is able to dissociate into more particles or more ions in solution, it will have a greater effect on the freezing point or change the properties more. So the freezing point of calcium chloride, since we know that the freezing point when we add things to our solution is going to go down, the freezing point of calcium chloride is going to be lower than that of potassium chloride. If we were talking boiling point, then it would be higher. So its freezing point always gets lower with a higher concentration or the more particles that are dissolved, and the boiling point always gets higher with the higher concentration or the more particles that are dissolved. Alright, the last one for the bit of help on this round of Castle Learning questions is actually a parts per million question. If you have 2,400 gram sample of an aqueous solution that contains 0.012 grams of ammonia, what is the concentration of ammonia in the solution in parts per million? So our equation is mass of solute, and this is directly from your reference table, over mass solution times 1 million. So that's 6 zeros after it. Okay, so figure out first off which one's your solute and which one's your solution. This problem makes it pretty easy because they give the wording right in there with it. So we have 2,400 gram sample of a solution. So we know that 2,400 grams is actually going to go down here. And the mass of our solute, in this case, the smaller piece, we're trying to find that is going to be our grams of ammonia. So that's going to be up here above our 2,400 grams of solution. And this is the biggest mistake I've been seeing students make, is they forget that 0 after the decimal point, which will throw your answer off and actually provide you with the wrong answer. So when you do this, it's 0.012 divided by 2,400 times a million. And if you don't have those decimals in the right spot, you'll get the wrong value. The correct value is 5.0 ppm. If your decimal's off, you'll end up with 50 parts per million. So you want to make sure that you are careful as to exactly what you're writing in there and how you are putting it into your calculator. And there is some help with this Castle Learning section. Hopefully this helps. Good luck. See you in class.